So I will not show the experiment that I did in real life because, well, I had a lot of up and downs, a lot of problems, and I will discuss all the problems on the way of the movie. I will show you only the good parts, and I will mention the bad parts as well. So what I try to do, pretty much the project is, my project is to drive this dingling. Uh, it's a single motor inside. That's it. And I dragged two wires, these green wires that you're seeing here, these two wires from the motor, and from the motor, the axle of the motor is spinning this. Is a surface that is moving left and right like that, and is cutting the beard. That's it. It's a very simple device. My friend gave it to me. He was throwing it away on the garbage, literally. Uh, and he thought of me, and he bring it to me and asked me, "Do you want this piece of shit?" And I said, "Yes, of course. Give it to me, and let me see if I can repair it." And originally, it had a battery inside, and that battery was an accumulator. It was having a charging port where you were plugging this little black plastic is in the end of the device, and this little thing was connected to that charging port, and the transformer for that charging port was 100 milliamps. I'm not kidding you. It was 5 volts. I'm not sure how much voltage it was. Probably 5 volts, but the amperage was 100 milliamps. That's it. If you wanted to drive the motor from that power supply for the charger, the power supply was could very easily blown up. This is the original transformer for the dingling device, and as you can see here, is says the output is 4.5 volts at 100 fucking milliamps. It's incredible shitty, incredible shitty. If you were powering something more demanding, the motor itself, if you were powering from this transformer, the internals of this transformer were blowing up. Something for sure is blowing up. This is made only exclusively for charging the accumulator inside the device, the dingling. And this is the accumulator, the original accumulator that was gathering a lot of white. I'm not sure how well can you see. It's a white oxidation that is coming out from the battery, and it was rusting the metal around it. And I managed to clean it and to cut it because it is spot welded, and I couldn't get it out easily and nicely. I had to cut it from both sides. And this is the accumulator. This is the markings on it. It is a nickel cadmium accumulator, AA, at 1600 milliamp hour at 1.2 volts. So this was powering the entire motor that is inside. This is the disassemble device. Here is the motor. I literally linked two wires on the motor directly, and I took them out through these two holes that is having here. Originally, these two holes were the contacts to the charger. This is it. This is all the device. And here on the button, on the movable button, I put everything in a bag, not to lose them. This was the entire board inside it. It is having a LED and a resistor, and this LED and resistor is used to signal that is making contact when you plug this device into that charger. This LED is telling you that is making contact. Here was the battery, the accumulator, on this long strip here, and here in this bigger hole. And from here, from this cutted wire and this cutted wire, where this was the connections to the motor. And here, as you can see through the board, this is a copper track that is coming from here, the copper track, and is going here as well. And here is a space between this pad and this pad, but here is nothing. So here was the button that was sliding, was making contact between this pad and that track, and this was making contact between the motor and the positive rail, pretty much, and the negative rail was connected to the motor all the time as well. And it's a single diode for probably for rectification. I tried to repair this motherfucker, of course, and I failed it. I couldn't. It was too shitty to repair it, and yeah, I couldn't repair it at all. And I didn't had an accumulator to change it here at all, the same size and everything, and on the same milliamp hour or better. So I decided to switch it to a wired device. That's and these are the two pins, metallic pins that were inside here and here, and these two pins were making contact with a charging port, and you can see how shitty how shitty this. I'm also curious about how it's made. This is a NPN transistor because I did try to reverse engineer it. Right, but that's it. This is it for the transformer and the battery and the interior of the how it's working. Okay. All right. I actually tried to reverse engineer this motherfucker. This very shitty. Let me actually show you. So this name, you see, it's AC to DC adapter, very small transformer, 4.5 volts at 100 milliamps is the title of this folder. And these are the components. I made a couple of pictures here. This is the track behind it. These blue wires are the 220 volts that are coming, and these black two wires that are going into the that little board that you've seen for the motor. And this is the a better view of the what you are interested is this part here, the output, what voltage and how many milliamps is giving. And this is a capacitor 1 kilovolt, and this is another one, and that's the transistor there. Yeah, 13,001. And this is the motor that was driving. Actually, is the board was charging the board. This is the board that was charging, and the board was having that accumulator. And this is me tracking down the circuit, and this is the actual circuit diagram that I made it in Photoshop. I converted all this mama jumbo that I'm having here into more readable circuitry. Is only this part, the transformer. This top part is this board that was inside with the accumulator and the wires for the motors. So is this top board here. So I'm showing that is going out 100 milliamps at 4.5 volts is going out into that smaller board. So that's pretty much it. This is the capacitors that you've seen here in the pictures. This blue capacitor and another one here, this guy here, and this 10 nano and this 10 nanofarads. This is a NPN transistor or resistor. This by measuring, I imagined how the windings are inside this transformer. I tested them with my digital multimeter on continuity and probably on resistance as well. Of course, very, very low resistance I was getting. I don't even remember what resistance I was getting. But this configuration that you are seeing here, at least at this point, I'm not completely sure how correct it is. I know for this end it is absolutely correct because it's only two wires. But here I wasn't very, very, very sure how everything is connected inside. But by the look of it, it looks like they are connected. So the current is coming in through here is only half waved with one diode here is letting pass only half of the wave. So it's 120 volts regulated with only one diode there, and this is regulating a little bit more here in this upper circuit. It's a very simplistic. I actually love very simple circuit. I love them very much actually, comparative with very complicated circuits. And this is it about this circuit diagram and how everything is connected. So that's about this device. And in all my tests that I did, let me actually show you. Here is the first test. Of course, I didn't put this large heatsink from the very beginning. I put a very small heatsink. Yeah, here. So here are my first tests that I did. I use this circuit diagram that you are seeing here. This is the voltage regulator here, where it says in, out, and adjust. I didn't write it. I should have. And then I used two transistors. I looked in the datasheet of LM317. And I find this circuit diagram. So this is NPN, and this is a PNP 682, BD681. This is the NPN, and it didn't work. I mean, it did work. No, I eliminated the NPN and I leave the PNP. And they heat it up, especially the LM317. It heated up very, very much. This is the motor inside. Is not actually 300 milliamps. Is running without a load, without putting anything on the axle by itself, but 1 amp with load. This is what is written there, but that's not actually correct because it's 1 amp and 44, or probably it's a bit more complicated subject because I tested this with everything holding in my hands when I write this down, these values here, especially the load, 1 amp for load, minimum 1 amp. But after I managed to repair the head, let me give you the entire device. So this black head, I had to screw it to repair.
All right, I told you it's a complicated project because here it is. So I hope you can see well enough. Here it was a plastic. It was a plastic here. It was made from plastic. And I cut a piece of metal sheet. As you can see, I bend it in place. And I bend it into this shape that you are seeing here. I also grounded until I matched this contour, round contour that is having here, plus this little notch that it needs to have that notch because it's having a guidance somewhere. I don't know where. Probably here. You see this line here is like a guidance to fit everything on the same line. And then I made two holes, very small holes. I believe 1 millimeter diameter hole here and here, and I used 1.2 millimeter screws. What I'm having here is, and I literally eat the plastic while I was screwing them, and I make room and I make the thread with the actual screw into the plastic meat that I'm having there. And it worked. It is holding all this metal sheet shape that I'm having here. Another problem was that it is having, I'm not sure how well you can see it there. You see it underneath is a nut, is a square nut, and that square nut, its hole must coincide perfectly with the hole of this little bended shape that I'm having here. And this is the screw that is passing through this moving head that I'm having, is going through here, is getting out through there. It must catch into that nut that is on this other side, that I super glue it. The super glue is not heat tolerable. If this metallic, if this metal shape that I'm having here is heating up too much, like not too much actually, like 50 degrees Celsius probably, the super glue that I used is getting off, is peeling off very easily by its from its own weight. It's getting off. So when I was grinding this metal sheet, I had to re-glue that nut there probably 3 or 4 times until I'm having it as it is right now. Plus the bending around, because I didn't bend it correctly the first try. I had to re-bend it a couple of times, and yeah, it's working now. This is the epoxy pole that I used, and it's not really that good. It is good, but you must be careful with it. If you hit up the surface that is gluing the two pieces of metal, it is getting off extremely quickly. It's very shitty from this point of view. So that was a very big problem. Pretty much this is it about this subject. And this is the actual head, and how, and I got inside, I managed to take out this this element, plastic element here. Here is a crack. 1 second to zoom in. And here is a crack. And this is the crack that my friend made it. Do you see the crack? My friend cracked it and then give it to me as a gift. And he didn't mention anything. I had to figure it out. So I managed to take out this plastic element and get inside. I will not open it because it's quite hard to put it back. But pretty much, if you pay attention, there is a hexagonal, let me zoom in. It is barely visible, barely distinguishable, but it is like a hexagon hole. And inside that hexagon hole, I managed to put a key, a hexagonal key, and unscrew it. Right now, I eat the metal around it while I was figuring out how the hell can I open it. And after I managed to get inside, I see that is a very strong spring inside, very, very strong. And it's making, you see, if I'm moving this, it's making this hole, this entire thing move back in its original position. You see, if I'm pushing it up, it's moving back. But it's very, very strong. It's very strong. It's quite strong. Here it's having like a triangular shape. You see, it's like two little dicks moving, staying up like that. And between them, this rotor shaft is moving them pretty much. Okay, it's moving them left and right, and it's creating this oscillation. You see, left and right oscillation of the blade. This is the mechanical part of the device. Okay, all right. I hope you like it.
This, my friend, he escaped this device in its head, and the plastic inside cracked, totally cracked. And he tried to repair it. He tried to glue it with Relandez, is a very, very good glue, and he couldn't repair it with that, and that's why he gave it to me. But after I managed to repair this head, I kind of squeezed everything and misplaced it a little bit. Is my opinion. I have no idea what I did there. I mean, in the sense that how it affected the rotor of the motor. So that's the problem. The rotor of the motor right now, in my opinion, is centered. Where the fuck are you? Where the fuck here? So this rotor of the motor is theoretically centered, but it might very well not be very centered. So that's why in my original tests that I did, holding everything in my hands, it gave me 1 amp when it was loaded with that head. But now after it is screwed and permanent, fixed there, is giving me 1.4. So probably, most probably, it is a misalignment somewhere. I have no idea where. And this rotor here is doing a little bit more work than it was when it was original. So when it was original, it was perfectly centered. I have no idea how they did it, but they did it. They perfectly centered it. But my repairment didn't perfectly center it. So it added a little bit more amperage to push the motor a little bit more harder. Probably, it's my guess, but I might be wrong. Maybe by holding it in hand, I was holding it loosely. Probably, I have no idea, and that's why it gave me only 1 amp instead of 1.4. So this is one side of the story, and this is important because if you have to drive something, you have to test the shit out of it, and it's exactly what I did here. Okay. Then, so this is the setup that I had. So make abstraction of this NPN that is on top, because this, what I'm cutting right now, this, I didn't use it here in this setup that you are seeing on my breadboard here. So the setup that I'm having here is only this part here, okay, down here. This is the circuit that I'm having on the breadboard without that transistor, that additional transistor, because it didn't. I did use it. I did try it with this transistor as well, and the LM317 regulator was heating up as nothing was connected here. So this was staying cold, and theoretically it should have conducted more current and heat up itself. These two transistors should have taken the wattage and the temperature over them, and not letting the LM317 to heat up. That's the idea of them, to drive more current through this transistor, and it didn't work in this setup that I'm having here. So this is 317 here, the first one, and the second one is this PNP 682 BD682 is this second one, and it's here. And I put these heat sinks on them, and as you can see, they are very, very small. This is not a correct size heatsink for this setup. This 320 milliamps is when it's running without the load. But when it's loaded, was jumping to 1 amp. The problem with this setup, what I'm having here, it couldn't move this head. Here is before I repair it. And this head, spinning head that you are seeing here, was between them and is moving them. And beneath it is a very hard spring, very hard. And that spring is making this moving jaw, to get back, and actually make the cutting. But it is having a crack here in the plastic. It is not very well, you cannot see it very well, but it is a crack there. A sign that this entire device was escaped from my friend's hands on the floor, and somewhere it landed on this head, probably, most probably, and it cracked from there. And also it cracked this part here that is not visible right now, that was holding the nut in which the screw was screwing. So I had to repair that shit as well. And now it is okay. It is okay. As you can see, there is nothing inside, absolutely nothing. You can see the two wires here connected to the motor, and you can see them there, and they are getting out here. And what I have, I measured the coil resistance, and it's 0.6 ohms resistance of the coil. And you will see later that the voltage is dropping. I hope you can see it, or I was discussing this problem, that the voltage is dropping to, from the voltage regulator, is dropping to 0.6 volts, exactly as the resistance of the coil of the motor. That's the voltage regulator is not maintaining to 1.5 or 1.2 as I was setting it up. As you can see it here with two resistors, was dropping the voltage as well when I managed to make it work correctly. In my latest tests, where is the here? When I was getting in this setup, this is the correct setup. When I was getting 1.42 amps or 1.44, it's supposed to regulate to 1.5, but when I measured this 2 points here to get the voltage over the device, it gave me 0.6 volts. It's a very interesting project, I'm telling you. Here, in this setup, let's say my friend put me to measure the output of the LM317, and I was getting exactly 1.508 in this case, but exactly 1.5 volts. It wasn't delivering enough power to the motor. The motor was it was under 1 amp. When I was using this very setup that you are seeing here, for a brief time it worked. I don't know why it worked, but it worked with this setup that you are seeing here the first time when I tried it. But after keeping everything here and testing it further in longer time, it started to, the motor started not to work properly. It was going down in efficiency, and it couldn't drive the load. That head, that moving head, it couldn't drive it at all. And that was a very, very big problem. And here I made a couple of tests. This is a strange, very, very strange experiment that I had. As you can see, it is mounted on a breadboard, but here in my final setup, it is not on a breadboard, and that's for a very, very good reason. And I had a very good and big luck to get it like this in air. You can even see the value of the resistor. It says there 150 air resistance, and this is 30 ohm. Here you can see orange and black. Even if it's very, very pixelated, you can still see it. All right, so I was very, very lucky because my friend from UK, he actually figured it out or remembered it probably, or he knew it, but he didn't have time to explain it, or he only showed me his setup there in his England, and I pretty much mimicked. I double it here in my Romania. I make it as I've seen it in his side directly. Everything is directly connected to the pins of the LM317. This is the winning circuit like this, in this form, in this shape, compared with the circuit I was consistently and insistently doing it on my breadboard, because I was trusting my breadboard. And with this project and with this occasion, I find a very, very big and important flaw of the breadboard. The breadboard is not made for high amperage and high power circuits, but this circuit was special because it is using very small values, like 1 ohm. You will see it in a second. You can see it even here. Yeah, you see, this is the real setup and what this wires means. But I had here a test before I put the motor. I tested it with a resistor of 1 ohm. You cannot see its markings, but trust me on it. It's 1 ohm resistor at 5 watts. It got warm, not hot, not completely hot. Hot is over 100 or over 90 degrees Celsius. But this was warm towards hot, not completely hot. You could keep your finger for a couple of seconds. And after a couple of seconds, of course, it was too hot for your finger to resist. But it was not like you touch it and immediately burned your skin. It wasn't like that. But this was a helpful, very, very, very helpful setup with the load as a resistor here. So that was preliminary. That was before I tested it with the motor. So let's get back. I know I'm jumping from past to present. This is the present here. This is the working setup. This is the past setup that I had, which is wrong, which is bad. But it's good to make a comparison between the two stages and to realize and to see from my experience what worked in my case and what didn't work and what I struggled to make it work. So here I actually made better images. I took this image and this image, and I made one single image with them. I believe I have them here. Yeah, I have them here. As you can see, it's the same image, and I even marked the location, the rail where everything is connected together. So the pin of the motor, this is to negative, is staying here to negative, this other end of the motor, negative rail. And this, I was jumping this wire all over the place. And read this amperage here. It says 0.69 or 0.7 at this junction here. Okay, this wire is not connected to anything. This wire is not connected to anything. Only this wire, this is the connection that I'm having here. Let me actually draw it. So from here, from this point where I put the probe here, then through this yellow jumper, then when it's reaching this rail, tiny rail is jumping through that orange jumper there, and then it's the wire of the resistor here, as you can see. But it's the rail of the breadboard that is connected to the middle pin of the LM317, which is the V out pin. Okay, and this is the V in, the rightmost. The number 3 is the V in, and you can see the yellow jumper that is coming from the plus 5 volts on the other side. But you cannot see it right now because it's this large heatsink here. So this is the track of the current. So theoretically, it should have been the same current everywhere, but you will be amazed, as I was. So here on this rail is showing me 0.69 amps or 0.7 amps if you want at 5 volts. Next, from here, I move it here, more closer to the pin, pretty much. And I was getting 0.70 amps. Okay, we can argue that 0.69 and 0.70 is the same. And I agree, it is the same. Maybe it's not a drop here along this wire, jumper wire. But I believe it actually was. And that 69 was even lower, 68 in some cases. Next image. Now I jumped here on this rail. As you can see, the wire is connected there after this wire link, orange wire link. And now it's 0.84. It jumped from 0.70, from 700 milliamps to 840 milliamps. Right now, just by moving it from this point here to this point here. Come on, come on. It's something very, very fishy, very, very weird. Something was extremely, extremely fucked up, pretty much. Why this jumper link here was dropping 140 milliamps over it. And indeed, this was the reality. This orange link, this yellow link that you are seeing here from the positive power rail, and probably this wire as well. I don't remember exactly, but they got scorched. They got scorched. The plastic got melted on them when I after some higher power tests that I did, not with this particular test that I'm having here, but other tests. So I managed to melt them because when I put my finger on this metal part here, it was extremely hot. And then I put my probe on it. I didn't make a picture. I'm only telling you from my memory. Was reading 150 degrees Celsius. It was reading on the jumper here, on the jumper, between 100 and 150 degrees Celsius. And probably in Fahrenheit is 200 something. So now let's jump even closer to the V out pin. So remember, it's 0.84 and next one is 0.9. When I'm actually touching this aluminum heatsink that is directly connected to this large pad, and this large pad is actually connected to this middle pin of the LM317, is absolutely the same piece of metal here. What we are seeing. Let me actually draw it for you to actually see what I'm telling you. So this is the current path that you are seeing here. So in this situation, I'm getting 0.9, 900 milliamps. And this was very, very, very fucked up because it didn't have sense. But after some days, this project took me a couple of days actually to be able to make it right. And I was very lucky of my friend because me alone, I couldn't solve it alone because I was stuck with building it on breadboard. Because and then I had the idea. I didn't have it myself. The idea. A friend. I was discussing this problem on AAC forums, which is I believe is an American forum for electronics. They are very good guys. They're very, very helpful. Some of them, not all, but some of them are very, very helpful. Especially the UK guys, if I'm not mistaken. So here I tested without the motor, and those guys from the forums give me the idea to use 1 ohm high power resistor instead of the motor itself, because the motor was giving me a lot of variable amperages here. It was not consistent all the time. So not talking about where I was linking, like I showed you before, but also in the same point, it was changing a little bit after I was powering up or powering down and then powering it up again. It was giving me totally different amperage with the motor. I have no idea why. Probably the overheating of the LM317, the regulator itself, was creating some sort of, I have no idea, surges of some kind or resistance of some kind. I have no idea, but it wasn't consistent. That was the problem. And when I seen the example, when I read about when I was discussing these problems, and most probably some guy gave me the idea to try with a single resistor there. In real life, he built it the proper way, but I couldn't catch it. This is the proper way. He built it in air like this, but I didn't get the idea from the first time when I've seen it on his table. And then I built it here on my breadboard here, and I was getting a consistent 0.62 amps with this arrangement that I'm having here, and it should have given me 1.5 because I was getting 1.5 volts if you remember. Okay. Oh yeah, here. So here as you can see, I was getting 1.5 very well, absolutely fine. So it should have mimicked that 1.5 volts to transform it into 1.5 amperes, pretty much. I should have seen here 1.5, not 0.62 amps, like you're saying here, or 620 milliamps. So that's this gives me another hint that something is wrong with my setup. But I was very, very slow in changing from this setup on breadboard to solder everything in air, like is the correct way. I couldn't do it very easily because I'm very used to do everything on breadboard. So my friend from UK, he showed me his this is his setup that he built it in air. As you can see, is everything soldered in air and with wires, with resistors, everything. And this is his aluminum heatsink, and this is the voltages and the amperage. I'm not sure. Here is showing 1.4 amps, and this is probably volts, 1.5 probably. Yeah, he's repairing this kind of old devices, old multimeters, and he is very proud of them. He doesn't want to give anybody anything. He is having a lot of them. He kind of hoard them, and he's repairing them. And I asked him for one, and he said no. He's an old dude and very cool guy, very cool guy. And this is a very retro multimeter. Probably not many people have seen this kind of multimeter here. Very retro, and probably very easy to use, I guess. I'm not sure, but he's trusting it with his heart. He's very attached to this kind of multimeter. Although he's having this fluke that I never had a fluke, or I will never have a fluke. I will have mine, the stuff that I'm having there. Okay, so this is his setup that you are seeing. This is another picture. And I modified. I put this text labels to get the idea which is which. And this is his 1 ohm load after he saw my sketch, my picture with my 5 watts 1 ohm resistor there. And I believe him. He got 1.5 volts V out on this blue wire at 1.7 amps. So wow, it's way over the limit of the LM317 regulator. The regulator is up to 1.5. But he was up over the limit a little bit. Probably you can, if you have a very good heatsink here. Yeah. Remember when I was showing you, let me get back here. Yeah, my first tests. Do you see this shitty heatsinks that I'm having here? He was laughing on me. He told me, oh, no, don't use this kind of heatsink because it's nothing. It's nothing. And I couldn't believe it. I couldn't believe him when he told me that these heatsinks are nothing. And after I made my tests and and I was showing him my large heatsink that I was having here, and I was testing myself, and I was getting some better results with this larger heatsink. And after I've seen his heatsink, aluminum heatsink that he's having here, holy fucking shit, this needs big stuff. He needs this regulator, this LM317. It needs a very, very big heatsink, very big. And I start to believe that this regulator, or all the regulators, probably all the voltage regulators, are made to be used with very large heatsinks. So that's the idea of a voltage regulator, to be used with very large heat conductive heatsinks. So that was a wow moment for me, at least. And this is the actual circuit that I built it. So he built this circuit in his real life example here. And then after I've seen his picture on his data from the multimeter here, and then I said to myself, well, if nothing works on my breadboard there, because I was getting 0.6, way less than 1 amp, and I also scorched the links here. The plastic was scorched, and I probed the link, and I was getting 100 over 100 Celsius temperature. Then I said to myself, well, if he got it to work in his side, I should try it with his circuit that he's having here, with his values, and this was a genius idea from my part, to actually mimic exactly what he did it, how he did it here. In reality, he built it in air, and I got off from my breadboard, so I leave aside the breadboard, and I built it mine as well. Where are you? I built it mine as well in air. As you can see, everything is in air, exactly how the idea he used, I use it as well. Here I was showing the links on the other side. This is the positive link. And here is a close-up for the resistor values that I was using. Everybody, including me, was thinking that in this setup that I was having here on the breadboard, we all thought, we were very, very certain at some point that my LM317 batch that I got were not good, were bad voltage regulators, because of the results that I was getting, consistent results that I was getting. Under one, I couldn't raise it over 1 amp, or even getting closer, but it was getting lower in amperage as long as I was testing it. So I was starting to believe it is busted. I have a lot of busted voltage regulators. And here I was, my friend told me to change the resistors. Maybe the resistor values were too high that I was using. I don't remember what. Yeah, this is 1 kilo, 1, 0, and 2, 0. And then the golden mark here. And this is 200 ohms. So 1 kilo and 200 ohms is what I was using. He told me to use way less resistive values here, although it didn't make sense, because if you put low resistance here, you let more current, you leave more current to pass through the adjusting pin pretty much, and all the power that I need is through V out. So it didn't make too much sense, but I did it as he told me to do it, and it didn't make any difference. Changing the resistors values didn't make absolutely any difference. This is another view to see on the other side how it's connecting there. Here I moved even closer the alligator clips, as you can see. I moved it closer to this entire to the LM317 because this red wire, well, both are red, but this from here to here, let me actually draw it. This longer wire here from here that is uniting the positive rails. This is positive and this is positive here, and this is negative and negative in interior, but on exterior it's positive and positive. This specific wire for the positive rail was getting warm. Wasn't getting hot, but it was warm. Warm like, I don't know, 40, maybe 50 degrees Celsius probably. But, safe to touch. And that's why this picture is here, because I eliminating those wires that were on the other side of the board that were getting hot or warm, and I moved everything, the alligators, very close to the pins of the voltage regulator here. And this gave me another result a little bit better, if I remember right. It was better this way than a little bit better, but not very obvious. It was like a couple of milliamps difference. It wasn't very obvious. Next, here, this is with a transistor actually, with a BD681, the NPN transistor. As you can see here, this is the circuit actually. The 681 is the NPN. I should have written here. And this is the setup that I used there on the breadboard. I put a diode here, a capacitor there, and here the base resistor that I was changing it. And this 1 kilo in this situation, but I was changing it numerous times. And I also have a LED under resistor. Here's the diode. This white thing here is the diode with very long legs. And this is the resistor for the LED that I didn't include it here on the diagram. This was good, the signal LED. It was staying off all the time while this was running. If I was disconnecting the wires, one of the wire from the motor, the LED was lighting up. But as long as the motor was connected to this links, the LED was remaining off, as it is, as you are seeing here. It's a very good advertisement LED, to tell you that something is wrong. So this is the actual circuit that I made it here. This is the circuit. You are seeing here, I used a 150 ohms resistor, 30 ohms resistor, 100 nanofarads, and 1 ohm 5 watts when I was testing the resistor load instead of the motor. And 1.2 amps was passing through the entire circuit basically, because the amperage I'm seeing it here from this power supply amperage meter. So as you can see, 1.21, I'm not lying. When I changed the heatsink here, I was experimenting with smaller heatsinks. So this is the good heatsink, which is large and thick. This is very important to be thick and very large. Here with this thinner heatsinks and smaller in size, even though I made like a burger here. I put a heatsink on top of it, and the voltage regulator is actually the metallic pad is flush with this larger aluminum heatsink, and I've added another aluminum here on the back that is like a corner there, and a long screw that is passing through all of these three at once. And they are moving a little bit too easy because it's only one connection, that screw there, which is not actually catching very well in the threads of this heatsink that I'm having here. This is threaded, that hole is threaded. So this is what I'm getting here, 1.44, a little bit more amperage than here, 142 with this larger heatsink. And I made some measurements here. This is from the forum, and nobody corrected me on this mathematics that I'm presenting here. And remember, I'm an artist, I'm not a mathematician. It's not that much of a deal what we are saying here, but I'm not doing it every day. So I was a little bit skeptic if this is good. But nobody corrected me, and I believe it's good. Or nobody looked at it. I have no idea. I have no idea. But I believe it should be good. And my friend from the UK told me to get rid of this bullshit that I'm having here, and switch to this bigger and better and thicker heatsink, because this is how it should be. And I had to learn the hard way how big the heatsinks should be, and I'm starting to get used to it, to this idea that it really gets very big heatsinks. And also another point here is that I put my probe here exactly here in this corner here, between this element and this surface here. I put it there, and I got this about 60 degrees Celsius. It was much more hotter inside, very close to the core of the regulator than a couple of millimeters, 1 or 2 centimeters away of it. Probably it was 70, 65, 70, 75 maybe. But it wasn't 100. That's important. It wasn't 100 degrees Celsius. And also I tested the real transformer that I will use. As you can see, all this time I use this variable power supply that I can change the knobs here. But now I have to use a single dedicated power supply to actually to make it portable, to walk with this device to my bathroom to plug this its power supply transformer into the wall, the switch mode power supply box into the power LED that is having there, and make it work and not fuck it up. The next design challenge is let me get back, because I will use this very large heatsink. And my friend from England actually told me to put a fan, a ventilator to blow cold air, but that is I'm not completely sure if it's a good idea. I have to test it. But it is a the next challenge with this regulator is to add the switch mode power supply box to make a box for this circuit that I'm having here, also to secure all these wires, not to make any kind of short circuits, and then the wire, that a very long wire to my device to actually use it. So this is the next design challenge, and I have no idea how to do it. I really have no idea how to do it. And if I will have to add a fan to blow on this heatsink, holy fucking shit. Yeah, that's a bit too much. That's a bit too much. But it's interesting. It's a very interesting subject, and I really wanted to learn about it. And I did push it to the limits. This voltage regulator LM317, I pushed it to the limits, and I didn't get over the limits. I push it very near to the limits. 1.44 amps or 42 amps is very near the limit of 1.5 amps that this is designed. This voltage regulator is designed to actually work. So I'm quite in the ballpark, I may add. I am very in the ballpark, but on the limit of it, which is good because it's excellent from multiple points of view. So this is my video, this is my presentation, and this is my experiment, and this is my demonstration. And I hope it will help somebody else. The explanation from my point of view, why was it lower amperage when I was getting this 0.9 instead of let me get to the resistor here example. So this 0.62 instead of 1.5 amps with the resistor. Why I was getting this value here? Because multiple power drop on the breadboard, like little shunts. These little wires that I'm having here, this orange one and the power one that is on the other side, and the red one on the margin there, they act like a shunt, and they are very sensitive to very small resistance. So this circuit is very, very special because it was using very small resistance loads. 1 ohm resistance is very low resistance, and usually what I'm using 10 kilo, 1 kilo, 100 kilo, why not, even 10 mega in some rare occasions, but usually 10 kilo, 1 kilo in this range. Rarely I'm going down below 1 kilo, very rarely. And over 10 kilo also very rarely. So this range I'm using all the time, between 1 kilo and 10 kilo for all my logic circuitry that I'm using. But this is not a logic circuitry. This is very analog and a very power circuitry. It's power related. And I wasn't aware, I swear to God, I wasn't aware completely 100% until I checked with the temperature probe these links, until I put my hands everywhere to check the temperature, until I smell the heated metal, because these links were smelling as hot iron. Very interesting, this breadboard didn't got warm, not hot, not even warm. So it stayed cool all the time. So it is having a greater power resistance than these links that I used here. Don't ask me why, but it is from my experience. So I was reading actually a friend from those AAC forums, very, very interesting idea he had to give me some links of breadboard characteristics and to read what are the limits for the breadboard. And if I remember right, it was 35 volts at 1.5 amps. This is the maximum limit for these breadboards until this plastic will practically melt, until that metal conductor inside is getting hot or even red hot probably. So you have to keep in mind that this breadboard is also having power specification, maximum power at which can work without damaging it, to keep it intact. So I was not over the horse with this project. I was not going outside of the nominal or normal functional characteristics of everything. I was quite lucky in a sense because I stayed under the maximum characteristics of this LM317 voltage regulator. I was in the limit of this breadboard and in the limit of these links. Actually, I scorched the plastic on these links, so I fucked up a couple of them, 2 or 3, and I'm very sorry for that. And I cried a little bit when I see the plastic melting. But I did my experiments anyway because I finally got it. So in a sense, I was very lucky on power maximum power for everything. I was testing everything with my fingers as well, and if something was getting too hot, I was reconsidering everything, and I started writing to people, I started talking with people, and this way I managed to make it work. In the end, and I was very very lucky of my UK from England my friend that he built it, he showed me, and I was lucky to be smart enough to replicate his circuit, and not only the circuit, electronic circuit, but also the implementation being in air and not on the breadboard. So that's it. I beat the horse enough here. I hope you understand this is a very important and interesting uh, circuit, and it's a very special circuit in my book. I mean, I'm not usually used with power hungry and super heated components. I hate heat in components. I hate it. For me, when I see a heated component, it's a sign of a problem, of a design problem. But this voltage regulator, they are designed to be heated up and work in very hot circumstances. It's designed like that. That's it. Thank you very much for watching. Your favorite artist electronist, Mr. Q12, and I hope you like it. Also leave a like, because this took me probably 1 week of development, of testing, of talking with my friends there, especially in UK. And also I want to show another thing. One thing I made this. Somebody else give me this example, come with his project. But so what he is having here. So I have a big GVC dead TV. So this is a TV. The brand is GVC. It's a very old brand. And here is the backlight. So he took out the screen of the TV, and these are the LEDs. Let me actually point it out. So this is the LED, this is a LED, and this is a LED, and this is a strip with 5 LEDs on it. And this is the backlight for the LCD screen. Let me get down. It also is saying here, it has 5 times 9 LED strips. So it's having 9 LED strips. So in this picture we see 1, 2, 3, 4, 5, but he is saying that it's having actually 9 LED strips, or probably 10. But 5 LEDs per LED strip. And the LED driver I purchased only went to 84 volts, and it needs around 120 volts. So he needs a power supply, SMPS, switch mode power supply of 128 to actually lit up all these LEDs. So the fix is to separate the strips. So pretty much he took each strip of 5 LEDs, and he put a voltage regulator per each strip. Very, very, very interesting project. I really like it. Yeah. It's about the wiring color. So he took 5 LM317 in his case, and this is the important thing. And a bonus, you see, and the bonus is the tab that he refers to. This is the tab that is having a hole inside. So it's screwed directly to the chassis for heat sinking, and the negative supply connection. So it's using this metal sheet that is having here for the heat of the voltage regulator to dissipate through the metal, and also as an electrical connection for the VA, it means output. So this is the output. This pad is the V output of the voltage regulator. 5 of these were used and screwed down using handy tapped holes. This is his circuit diagram that he's having. I'm going to run this on an old 32 volts HP printer supply. So he used this circuit diagram that you are seeing here. This is not actually a voltage regulator, classic voltage regulator setup that he's having here. He is using a constant current setup. So he is using the maximum voltage and is limiting, or better said, probably varying, only the current, not the voltage. Only the current is limiting through the circuit with the voltage regulators. So probably he is using all the 32 volts for the entire, for all the LEDs that he needs, and is varying only the amperage until the LEDs are lighting up. So that's each string is running at 125 milliamps, each 5 LED bar. He is repurposing this TV cases, TV with the LEDs as a very big spotlight. Pretty much, the metal sheet is used as a heatsink for the regulators, and also a support for the LEDs to be screwed in. And he is using a light source, but using that entire metal sheet, which is a bit too much, too large, in my opinion. You can cut to a certain dimension, not to use it as it is. You can cut it down and make it a smaller, more convenient, and more, a smaller dimension, because being so big, it's looking ridiculous, but doesn't matter, because this is used in above my work area, in his garage or something. In his garage, he put a little bit of light there, and he is happy with it. It is pretty big light. What he means is it's a pretty big dimension, 1.2 meters wide. So it's a 1 meter long screen, which is, it's a bit too big. That's why I suggest to actually cut it to a more normal dimension, not to leave it like that big. So This is my comments here. This is his comments. I am going to run this at 30 volts, 32 volts HP printer supply, and I actually I go online and I search exactly for this naming 32 volts HP printer supply, and I got this 32 volts at 1 amps, 1.5 amps brick power supply, like those old power supplies use, and it's perfectly fine. I really love this. I really like this power supplies because for if you use it as intended under the maximum amperage, it will hold 100 years. I never seen one defecting itself for the brands. I mean, when they were used correctly. But if they are used incorrectly, well, that's another story. I'm trying to understand. So this is me. This is me trying to understand his circuit, because in his diagram is showing this bridge rectifier here after the transformer, and also a smoothing capacitor as well here after the. I'm not sure. Probably he took out this circuit from somewhere and he adapted it to his needs, probably, and that's why he left this part. But theoretically, this power supply is giving directly 32 volts DC on these two lines. On here is the positive probably on the top, and here is the negative on the bottom. This I read it IOR, your, but actually it's 10 ohms resistors. This R1 is this rectangle is a 10 ohm power resistor, and probably at 5 watts you can barely see it there. You can barely see it there, but there it says 2R. 2 ohms at 5 watts, but he used 10 ohms at 5 watts most probably, or not even very much wattage, because I looked here. You see, this is not even 1 watt, probably 0.5 watts, 500 milliwatt resistor. It is not. I don't think it is 250 milliwatts. It's a little bit bigger than 250 milliwatts resistor. So this is probably 500 milliwatts resistor, a little bit bigger than that. But if I remember from my discussion with this guy, with this dude, he mentioned that you can use 250 milliwatts resistor as well here for that 10 ohm resistor, and because the power, he made a calculation, and I have it here. Yeah, I have it, and I will read it as well. Then you let's read along. Then you use a constant current circuit configuration for your LM337, because he is having another chip, which is the complementary version of my LM317. So exactly the opposite version for the negative voltage is this 337. Like this. This is the circuit that I find it in the datasheet of LM317, and this is for constant current. In this case, in this example, is for a battery charger, but he used it to power at a constant current these LEDs, power LEDs that he is using. The 10R, so that 10R resistor there in V out, and this is my explanation, what I'm saying here, and what I believe it's correct. I mean, what I understand from all of this, from his circuit. The current, the LM317 will be sinking is 1.2 volts divided by 10 ohms and equals 120 milliamps, and the power the 10 ohm resistor will dissipate is 1.2 times 1.12 times 12 milliamps equals 144 milliwatts. So a standard resistor is okay. By standard, probably he means 1 by 4 or 250 milliwatts resistor, but probably he used 500 milliwatts resistor. As for the LM dissipation, LM337 dissipation, it will be power supply volts minus LED drop times current. So the LEDs drop around 25.4 volts total. So all the entire strip of 5 LEDs, probably 5 volts per LED, 5.1 volts per LED, and 5 times 5 is 25 volts per single strip, and he is powering one single strip with one LM337. I do not know the LED's maximum current and that they run. Probably, yeah, of course, because they are pretty much scrapped LEDs. He didn't buy them, but using 120 milliamps looks okay, and suits the parts I have. So he was kind of lucky in a little bit. Also, the total current with all strings is 600 milliamps, and the power supply has a maximum current of a bit over 800 milliamps. So all should be good. So he is way under the maximum power supply. He is way under power consumed from the maximum power supply can give. I just have used 10 microfarads tantalum capacitors on all my regulators for many years with no trouble. All right, and with this I will close this very, very long movie. Unfortunately, sorry for that, but it's a very, very interesting subject, and I will leave you with my circuit diagram that I actually built and I used, and it worked, and I'm very, very happy and very pleased that I made it. I made it work, and this is it. Thank you very much, and see you later. Bye bye from your favorite artist electronics, Mr. Q12. See you later.
All right, and this is my dingling beard trimmer. It's a single motor there inside, and that's my LM317 somewhere there inside. I will have to change radiator, this aluminum radiator, with this other one. This will be the final one. This is here for testing only, and right now it's not powered from my power supply. As you can see, it's off, and this is
the alligator clips from my power supply there, and here is my this entire device, this entire contraption that I'm having here is from this wire that's coming from this switch mode power supply. And when I'm taking it out, let's check. I don't care what brand it is. It even it is even written in my language, in Romanian language. So current integral, it means input current of which is wrong, by the way. Alternative current 240 volts, and it's not about the current, it's the voltage. Okay, at 50 hertz, but in my country is 240 volts. It used to be 220 volts, like in China, but China remained with 220 volts, and Germany and Romania switched to 240 volts. I don't know why. Don't ask me why. I have no idea. The output current ieșire, it means output current, and this is what we are interested, and I am interested as well. It means DC, direct continue, or direct current. So it's a range 3.6 up to 6.5 volts, and it will deliver 3 amps between this range. But my voltage regulator that I'm having there is regulating to 5 volts. It needs 5 volts actually. It's regulating to 1.5 volts. And I'm not completely sure. I want to believe, I'm not sure what voltage is receiving. I can measure it actually, what voltage is dropping on my regulator here. I don't think it is dropping 5 volts like in my tests. But if it's in this range, between 3.6 and 6.5, so my 5 volts, it should be at 3 amps easily. And as higher as it goes in voltage, 6.5 to 9 volts range, it will deliver 2 amps, and even higher, from 9 to 12 volts, it will deliver 1.5 amps. And this is the minimum 1.5 amps for this switch mode power supply, SMPS. And my motor needs 1.44 amps, very, very close to this limit that is having here, but at a very, very low voltage. So theoretically, it shouldn't stress electrically and thermically this SMPS that I'm holding here. Theoretically, it should not hit at all. Nothing in it should not hit at all for the amount of power that this is drawing. Theoretically, but practically, who knows? I didn't test it on the long run, meaning I didn't test it for 5 minutes, or I only tested it to see if it's working. So the long run testing, I don't know, 15 minutes at least, and if it's resisting 15 minutes without doing anything, without burning up, then it's a good to go. You know, at least for me. If you want something much more, I don't know, durable, you have to test it for half an hour, 1 hour, constant working. You know, to work all the time. But for what I need here for my Ding-Ling beard trimmer here, which I will use it, I don't know, probably 2 minutes while I'm shaving my beard. It's good enough, you know. And the biggest problem is I will have to take it out from here and move it to this bigger and more suitable. This is more correct heatsink. This is not a correct heatsink, and I start to see the difference. And the difference resides not only in the how large the heatsink is also the thickness of it. You see, it's very, very, very thick compared with this shit that I'm having here. Well, this is better a little bit in thickness, but as thick the better, you know, and also large, and also to stay in the fucking middle here, not in a margin or on a side. Fix in the middle to radiate circularly. You have to imagine the heat that is radiating, and to leave space for the heat to surge into the metal and to cool down more efficiently, a little bit more better than when it is on the margin somewhere where the heat is forced only in 3 directions to go instead of 4. So yeah, that's it. I wanted to show or to prove that it is working fine. I had a ton of problems, and I will discuss about them. Or I did discuss about them already. I will discuss them in more detail soon. All right. Thank you very much for watching, and see you later.